Morning. Thank you for coming to the last session this morning. Today we have Neil O'Sullivan here from Google to talk to us about optimized power delivery.
Thanks so much, Mark. Very good morning to you. Thank you for coming. As Mark said, my name is Neil O'Sullivan. I'm the Platforms Power Team Manager for Google in Mountain View. And today I'm going to talk about optimized power delivery architecture for data center scale server applications. So to start, let's just take a little look at the context and the background. Data centers, cloud computing, are one of the fastest growing users of electricity globally and consume about 2% of global electricity use. To put that in context, that's about the same amount of electricity as a country the size of Spain or Italy. In the United States, the NRDC, the National Resource Defense Council, are predicting data center electricity use to reach about 140 billion kilowatt hours by 2020. Now, it isn't that there haven't been good improvements in efficiency, in data center efficiency, over the past number of years. I think all the major players like Google, Facebook, Microsoft, and so on that publish their PUE numbers have shown significant gains. But PUE is really facility level efficiency. And if you look at the definition of PUE, it's total power into the facility divided by the total power consumed by the IT. So it doesn't really tell you anything about how efficient your IT is. So in the book, The Data Center as a Computer by Luis Barroso, Jimmy Trederos, and Urs Huxley, they define a term called SPUE, or Server Power Usage Efficiency, which is the total power into the server divided by the total power used by the devices doing the work on the server. And that's what we're going to focus on today, because I think that's a particular area for opportunity and improvement. And given the massive growth we're seeing in cloud infrastructure, I think there can be significant impact there. So let's start by taking a look at what a typical server power architecture looks like. So the picture here on the right-hand side shows AC coming in to an AC-DC power supply, which is converted to a 12-volt output. And then that 12-volt output goes to voltage regulators on the server board, where it's converted to the point of load voltages. And POL, point of load, that's a term we'll be using a lot today to describe the chips and the memory, whatever uses the power, the end user of the power. So this is the typical type of server architecture we have today. Those VRs that convert from 12 to point of load, they are typically today multi-phase buck topology. And that topology has been around for quite a while, over 20 years or so, long before the proliferation of data centers and cloud computing. And I think it's served the industry well, and the industry has done a good job in advancing it to take care of the advances in the microprocessors and memory and so on that have needed new updates to support their needs. However, the focus has been very much on driving cost rather than efficiency. And for example, if you consider the AC silver box power supply, AC to DC power supply, that actually does have an industry standard. The 80 Plus group have driven efficiency standards for that. So there are actually efficiency standards for that. But as I said, with the multi-phase buck, the focus has been much more on driving cost rather than efficiency or density and so on. So the question then is, this is the technology we have today. How well positioned are we for the challenges that lie ahead, and what are those challenges? So this next slide shows a graph of how microprocessor technology has evolved over the last 40 years or so. It's put together from data from Horowitz et al. And Carl Rupp from his blog. And it shows a number of interesting things. First of all, we see those blue dots, those dark blue dots show how, single thread performance has been flattening off since about the early to mid 2000s. Frequency has been flattening off as well. And with the end of Dennard scaling, we've seen a lot of CPU manufacturers move to multi-core architectures so that they can provide additional performance growths on every performance gains on every new generation of processor. If we look at the power here, and bear in mind the vertical scale is a logarithmic scale, if we look at the power, there has been a steady uptick in power. Now, it hasn't doubled over the last decade, but I think we've seen tens of % increase in power consumption in a 5-year period or so. And today, our high-end CPUs consume about 150 amps current, and require and demand about 500 amps per microsecond of dynamic current. There are also new devices that have come along, like GPUs, that also consume several hundreds of watts. And so the question is, how well positioned is this multi-phase buck architecture to deal with this continuing trend in power, this uptick in power? And, is a 6, an 8, or a 10-phase multi-phase buck what we should be using moving forward? There are also some challenges at, I think, the system integration level. So again, this is the picture of our server, our 12-volt server power architecture that we have today. And over recent years, we've seen this server, change in its composition a little, in that the AC power supply has moved off the server and into the rack. And so now, 12-volt power is distributed from the AC power supply that's located in the rack to servers that are located all over the rack, right? And there's been a good reason to do this. I think moving the server off the tray into the rack means that you can have moving the power supply off the tray into the rack means that you can have redundant power supplies, which means you can increase your uptime or your availability. And of course, it also makes serviceability easier. However, though, now the 12 volts has to travel a longer distance to get from the power supply output to the actual server load. Previously, when it was on the tray, the AC power supply was on the tray, the 12 volts had to travel on a short cable from the power supply output to the server board. Now we see the 12 volts traveling from this shelf of power supplies through bus bars, through connectors, through jumper cables in order to get to the server. So increased distribution losses is a feature of this new architecture. One way you could solve or reduce these distribution losses would be moving to a higher voltage, for example. If you went to 48 volts, for the same load power, you'd have a quarter of the current, and therefore, based on the I²R rule, a 16th of the losses. So it seems like there may be some advantages there, but I think there are other things to consider as to whether going to higher voltage could be viable or not. And one of the things you need, I think, if you go to higher voltage is you need a suitable point of load technology. In other words, if going to a higher bus voltage means you're going to have to convert to an intermediate voltage to get to your point of load, you're introducing additional conversion steps and therefore additional cost and losing efficiency. So you need a point of load VR that can convert from your higher bus voltage to your point of load. You also need to have an ecosystem of components that can support that, because really you want to build and deploy at scale. You need suppliers who have expertise who can support that work. And also it needs to be reliable, have good availability, and meet safety, EMI, and all those other practical things that are required to deploy systems in data centers. So when you think about these features or these aspects, then actually 48 volts that I mentioned earlier seems like a reasonable candidate. From a distribution loss perspective, as I said, you will have theoretically 1/16 distribution losses compared to 12 volts for the same load power. I think there is a 48-volt telecom ecosystem in existence already. So you can actually buy rectifiers, hot swap controllers, DC-DC bricks. They're already there. And another benefit is you can actually, I think, have a more cost-effective and efficient UPS. So in today's 12-volt racks, a lot of them use a 48-volt battery. So you have to convert from the 12-volt bus to 48 volts to charge the battery. But probably the more impactful aspect is when it comes to powering the load, you have to convert from your 12-volt battery, your 48-volt battery, back to the 12-volt bus, right, to power the load. And generally, these battery systems are a couple of kilowatts. So that DC-DC converter that converts from 48 to 12 is a pretty sizable and expensive component. So I think, you know, moving to 48 volts, the electronics that do that function, that connect your 48-volt battery to the bus, can be a lot simpler and more efficient, and therefore you save on that aspect. But by and far, I think one of the biggest challenges of using 48 volts is the 48 to point of load solution. And particularly, I think, for demanding point of load devices like CPUs. Well, the good news is that at Google, we've solved this problem. And we've actually deployed our solution at scale on multiple generations of server. So we've proven it to be reliable. We've gained from its efficiency benefits, and we know it works. On the right, actually, is a picture of a rack, one of our 48-volt racks. On the top, you can see the AC to 48-volt rectifiers. In the center are the 48 to point of load payloads, servers, disk trays, and so on. And on the bottom is the 48-volt UPS. So it might be interesting then to go and take a step further and look at what does a 48-volt power architecture look like on a server or an IT tray. So I've shown a server here, but it could be for a networking tray, could be for a storage tray or anything else. And here you can see you have the 48 volts that comes in on the left-hand side from the bus through a hot swap controller. And then you have a direct 48 to point of load conversion for the CPU, another for the memory. And then in this case, I've shown an intermediate conversion to 12 volts for some of the other rails that are on there. But I think the main point here is that technology exists today for a direct 48 to point of load conversion for most of the VRs you would actually need on a typical server like this. But you might be asking yourself, well, why then did you pick 48 to point of load for the CPU and the memory? Well, that's a good question. And this graph, which again is from the book, The Data Center as a Computer, gives a clue to that answer. And this shows basically power consumption versus workload for a typical server. And you can see that most of the power is consumed by the CPU and the memory. There's a little bit of power consumed by the hard drive. And then there's the green section there is for other rails, about 15% at peak power, and there's probably about 10 to 15 other rails consuming that power, so lower power. So I think the reason, to focus 48 point of load on the CPU and the memory is these are the major power consumers, and therefore give you the biggest bang for your buck in terms of efficiency and dollar per watt cost and so on. So, okay, so I've talked kind of in general so far. You might be asking yourself now, well, okay, how much efficiency gains am I actually going to get? So here's a table that shows typical efficiency gains and a comparison between 12-volt architecture, 48 point of load architecture, and in the middle, a minus 48 type approach. So basically, I think you can see here that when you compare the 12-volt system to the 48-volt system, at least the 48 point of load system, the 12-volt system has at least 30% more conversion losses. And I'm only showing conversion losses in this table. It has 30% more conversion losses compared to the 48-volt direct-to-point of load. So obviously, when you start including distribution losses, you get additional benefits because they're going to be less with the 48 volts. It's probably worth mentioning a little bit about the minus 48 one in the middle here. When we started working on 48 volts at Google, our first prototype was a minus 48 volt rack. And we learned a number of things from this. First of all, of course, the obvious thing is that 48 volts, yes, you have less distribution losses. There's a benefit there. We also learned that, those savings from the distribution losses, well, unless you have direct 48 to point of load conversion, you kind of, what you gain on the swings, you lose on the roundabouts. Unless you have a direct conversion from 48 to point of load, then you really are not maximizing the opportunity here. Right? So 48 to point of load is a key enabler for optimizing the whole solution, the end-to-end solution. The other thing we kind of found out, and that's interesting here, is that we could have done minus 48 to point of load. You can probably see we actually chose to do plus 48 to point of load. Well, the reason we did plus 48 to point of load and not minus 48 to point of load is that if you do minus 48 to point of load, your point of loads are invariably positive voltages, plus 1.8, plus 3.3, plus 5. So when you go from the minus input voltage to the output positive voltage, you need an isolation barrier. And this introduces complexity and challenges, right? Because your control feedback between your output and your input has to traverse that isolation barrier. And so we basically decided on the plus 48 volts for that reason. It's not that you can't have an isolated plus 48 volt solution, but if you go with the minus 48 avenue, if you go down that path, you're pretty much making isolation a permanent requirement in your system. And we didn't want to do that. So that's why we chose the plus 48. It still gives us the opportunity to have an isolated system if we need it, but with plus 48, in this case, we don't need to have it all the time. So to summarize then, I think, plus 48 volt architecture reduces losses by about 30%. The key enabler is the plus 48 to point of load technology. And this does result in significantly improved SPUE. And by improving your SPUE or your IT efficiency, actually these benefits also ripple upstream. So because you're consuming less power in your load, because it's more efficient, you're drawing less power through your your upstream infrastructure, and the losses in that are going to be less because you're consuming less power at your load. So you get a good end-to-end benefit with that. So I think there are, to go back to the point I made on the initial side about global efficiency, global power consumption for cloud and data centers. I think improving SPUE. If we all improve SPUE, our IT efficiency as a community, I think we can have a big impact on reducing that global electricity footprint. And I think we can also save ourselves billions of dollars in kilowatt hours as well. So that's the talk. That's all I have to say. And if you have any questions, I'd be happy to take them now. See, we have a few enthusiastic questions. So I don't know who's first.
Hi.
Okay. You are, okay.
I have a couple of questions. First is 48 in general, like for human beings, is it safe to touch or is it just on boundary?
Okay, so the question is 48 volts safe for human beings? Well, 48 volts is categorized as an SELV, a safety extra low voltage. It's under 50 volts. Depending which standard, some standards say 60, some say 50. So it is safe to touch, yes.
Okay. So second question is for the like the motherboard, for example, like today if we have 12 volt, we probably in many kind of designing on the PCB, we can have a 3 mil separation per pack between them for material. So for that, drive the thickness bigger for the 48 volt, for the
okay. So
like 3 mil core.
The question is, so spacings, I think on PCB layouts for 12 volts compared to 48 volts. Yes, you're right. You asked if it would increase the thickness. I don't know if it increases the thickness, but it depends on your actual board, how complex it is. I think it definitely you have to have greater spacing
Sure.
between adjacent conducting paths, right? And that is higher so that creepage clearance is taken care of, and that you don't suffer from dendritic growth or those kind of adverse effects. But I don't think it's a prohibitive.
Right, it's something can be worked out.
Yeah.
Just something to work
I think it's, again, the telecom industry have been doing this for a long time. They have pretty dense boards, and I think it's perfectly doable.
Last question, third one last question is what's the chance you see on the drive? Like, do you think there is will be some effort or it makes sense to make the drive also take forward, because they are kind of the third largest consumer, and in general, basically whatever here it sounds like will be a benefit for server, but it will be a penalty for drive. For example, this drive they just use 12 volts today, 5 volts.
Yeah, I mean,
there will be 48 to 12 volt.
I think so the question again is, do we see 48-volt drives becoming a reality? And I mean, there's no reason why not is my answer. I think really you have to look at the whole TCO story, but I think there's no reason. I think the technology is there to enable it. So I think definitely something to consider going forward. Okay, I think you were next.
Actually, quick side question. Motivated by fish for our space. Google, I think you're going to see.
Yes. We adhere to whatever is necessary so we can deliver systems at large scale reliably.
Real question. So you have
I mean, I don't have that data here. So the question is, how does the 48 point of load efficiency curve look like, right? Because your load isn't always at the peak; it varies around. So I mean, yeah, you have to. That's kind of, I think, up to the individual application to optimize that over the workload, the power load range that your system is going to operate at. Yeah, I think.
well, and so actually, at the high end of that, the idea of where you get a comment at the very beginning about you made a comment in the paragraph that you go to multi-vector phase, but I'm not sure if it's as well as super high frequency.
Okay, so his question is about, my comment about, I guess my question was, is 12-volt point of load multi-phase buck the right topology to use as we see these increasing, as we see these increasing power loads? I mean, so the point is, right, the 12-volt point of load multi-phase buck, you have to keep adding phases if you want to increase, your, so that can take up quite a bit of real estate on your board, and there's other challenges with having a very large power converter. So I mean, I think it depends on your application, but that's something to consider, right, in terms of making a decision or a choice to go 48 or not. Yeah. Well, I mean, yeah, I didn't talk here very much about, why the multi-phase buck isn't used for 48 point of load, but obviously as a topology, that doesn't work for that huge voltage step. So when I talk about 48 point of load topologies, there are new topologies. It's no longer a multi-phase buck topology, right? That's for these 48 point of load solutions.
And actually, so on that note, who does do that? You comment
Yeah, I can't comment on pricing. I think there's we over the past number of years, as we've worked with our vendor partners to drive 48 point of load solutions, that there are quite a number of vendors out there now who actually do that technology. So I think some of them have actually done press releases around this event here today. So I think if you do a search, you'll see what's available. I think there's quite a few choices. Okay, thank you. I can't remember who's next, so whoever shouts the loudest gets to ask the question. Okay, this guy here.
So actually, I have 3 questions.
All three questions.
Well, very short, very brief. Okay, so I think you have 12 volts that come to 128 volts. Then the microprocessor is powered by 25 volts or lower voltage.
No, well, in this case, I was assuming that, sorry about that it's powered by 1.8.
So all the
I assumed in this efficiency chart that, these are 1.8 loads.
Okay, so, and do you have another state power conversion from 1.8 to lower voltage?
No, that's it. That's the voltage to the device.
Okay. All right.
They may be doing something inside the device. I can't speak to that, but this is the actual voltage to the pin on the device. This is just an example, right, for this case.
Okay. And another thing is all the you don't have isolation between 48 volts downstream. What happens if the core condition with the high voltage direction to the core? That's fine.
What happens, there isn't the 12 volt point of load. Multi-phase buck isn't isolated. What happens when there's a fault? You have to have protection on your motherboard, fusing and so on, to deal with fault conditions. But I think whether it's 12 or 48 isn't the major kind of concern, right?
My last question is, so minus 48 volts, the reason minus 48 volts battery related.
That's correct.
Then
Yes.
yeah, plus 48 volts, unless it's different battery technology, will you run into the corrosion?
Okay, so his question is regarding, minus 48 was originally used by, I think, some telecom. I'm not sure if it was used in some marine applications, but it was used really to combat cathodic corrosion. And, these were pretty harsh environments. Data center environments aren't that harsh. So I don't think we have that problem. So, we can basically then use some innovation, right, to take advantage of that. Okay. Yourself, yes. How many kilowatts do we supply to the rack? So I think it very much depends on the configuration, whether it's a disk rack, a server rack, whatever. So it really can vary quite a bit. What are they plumbed for? I think, we set them up so we can configure them for our different configurations that we deploy. Yes. I'll take, Lawrence, do you have a question?
A comment on the 48-volt hard disk. We'll actually be talking about revolutionary hard disks, including 48-volt hard disks later. So please come by this.
Okay. Well done, Lawrence. Okay. Yourself. So how many bus bars? So, why does that matter? I'm just trying to understand why you're asking the question.
I think,
Yeah.
this would be at 3 and then there's one. So I wanted to understand one bus bar or two bus bars.
I think that's a question. It's up to yourself in terms of how you want to design the rack, right? Do you want dual feeds to your payloads? Do you want single? I think you can have an efficient solution with a single bus bar. So I think, again, on this 48-volt rack, we're working with our partners in OCP. I think the proposal is a single bus bar, but I think there's no reason why you couldn't extend it to more if you want more. Yes, at the back.
Is this a proprietary board that you do anything, or is there any reference design?
I think the partners that on the 48 point of load, I presume your question is related to the 48 point of load. The industry partners we've worked with to develop that are free to share their technology with everybody. So it's available to you or anybody who wants to use it. Okay, the question is, are we going to write a white paper on this? I think we haven't written one yet. We may consider doing it if there's enough interest. So I think we'd be open to doing that. Okay. All right. If there's no more questions, thank you very much.